In the following pipe system, there are 125 feet of 2-inch pipe, 75 feet of 6-inch pipe, and 150 feet of 3-inch pipe. They're all cast iron with a relative roughness, a surface roughness of 0.00085. There are two 90-degree elbows and an open globe valve, all screwed. If the elevation at the exit is 0, what is the horsepower extracted by the turbine when the flow rate is 0.16 cubic feet per second of water at 20 degrees C, the density of 1.94 slugs per cubic foot, and a viscosity of 2.09 times 10 to the negative fifth slugs per foot second. The thing with this problem, the really interesting thing, is we have 3 different pipe diameters, which means that we're going to have to calculate out 3 different sets of total head loss. One for the 2-inch pipe, one for the 6-inch pipe, one for the 3-inch pipe. And then we'll have to add those all together into our total losses. So as we begin, let us first make assumptions. We know we're going to be using the energy equation on this problem because we're trying to find the power extracted by the turbine. So to use the energy equation, we need to make a couple of assumptions. First is that we have a steady flow, which we do have. There's nothing in the problem that states otherwise. Second thing that we're going to take a look at is we're going to assume a constant density, which we can do because we have water. Water is generally incompressible. And the third thing that we're going to do is we're going to assume that we have a constant temperature, which would make sense because there's nothing in this problem that says there's going to be anything but a constant temperature. So as we continue on, we take a look at this example. We've made our assumptions. We'll write out our energy equation. Pressure over gamma plus V squared over 2G plus Z coming in equals all of this stuff coming out, plus the total head losses minus the head of the pump plus the head of the turbine. Let's go back and look at this picture once again really quickly. So we're going to take our input is right here. So if we draw our control volume, we draw all around the piping system. Our output is actually going to be right here where the pipe is ejecting. Why aren't we taking the surface of the tank below it? Because at the surface of the tank below it, we can say, hey, there's no velocity, there is atmospheric pressure, and all this stuff. Because we have no idea where that tank is in relation with the exit. The only information we have is about the exit, which they tell us the entrance is above the exit by a certain height. Elevation of 100 feet. So what we're going to do is we're going to take our output right at the exit, so right as the fluid is leaving the pipe, which means it'll be at atmospheric pressure, but we do have some velocity there because that's the information that we know. So no pump, pressures are equal, no velocity at 0.1. This is what our final equation is going to be. And so we rearrange it for the turbine. This is what we have. The head of the turbine is going to be Z in minus Z out, minus the sum of all of the total frictional losses, minus V squared out 2G. So 3 pipes, 3 different sets of losses. And so what we're going to do is for each pipe, we're going to go through, calculate out epsilon over D, calculate out Reynolds number, calculate out friction factor, solve the Darcy-Weisbach equation for each individual pipe. So as we look at the first one, the 2-inch pipe, we'll call A, epsilon over D, we'll find to be 0.0051. I have L over D here just to make the Weisbach equation a little bit easier, so that's going to be 750. We can calculate out velocity today at 7.33. So throughout everything with the 2-inch pipe, we're going to be calculating out based on a velocity of 7.33. Once we go to the next size, then we calculate it using that. So if we calculate that out, that's a Reynolds number of 1.13 times 10 to the fifth, which is a very turbulent flow. So now if we go to the Moody chart, the first thing we do is we find that 005 line, which will be right in between these two guys here. And then I have to find 1.13 times 10 to the fifth. So here's our 10 to the fifth. So it's roughly right in there. And so what we're going to do is we're just going to follow that over. Pause this for a second. And the reason I pause that for a second is since I did not write the epsilon over d here, it's actually 0.005. So we're looking right about in there. So if we follow that out, have it track everything else, that one comes up, should be getting a Darcy friction factor of about 0.03. In fact, if you use the equation, it's going to be 0.0314. So from there, we're going to look at the second pipe, the 6-inch pipe. Epsilon over d, it's the same kind of pipe, but different diameter, so our epsilon over d changes to 0.0017. There's our L over d. We'll calculate out the velocity. Much bigger pipe, so it should go slower. So our velocity is 0.82. We calculate out our Reynolds number here, and our Reynolds number will be 3.8 times 10 to the 4. Once again, very turbulent flow. So if I look at my Moody chart, and I actually pull up the correct epsilon over d this time, which is going to be 0.0017, so somewhere right in about there. And then we're going to look at our Reynolds number of 3.8 times 10 to the 4, so it's almost 4, so it's going to be right about that line there. And we look at where those two guys cross. So this one comes over here, kind of sketching in between. We read it over the left. We'll find that our Moody is about 0.0266. Finally, we go look at our 3-inch pipe. This is our discharge pipe. Epsilon over d changes, so 0.034. We have a velocity of 3.26. This velocity is important because this is also our velocity out. So we're going to be using that in our main energy equation. Reynolds number, you'll calculate it out to be 75,600. So if we go to the Moody chart here and look for 0.03, we're sitting right about there. And then if we're looking at 7,500, so 7.5 times 10 to the 4th will be right in there. And once again, we just look where those two cross. We sketch this guy out here. Crosses about right there, which gives us a Darcy friction factor of around 0.0287. So now we're going to start looking at our minor losses. Now we've got a couple different minor losses. We have minor losses that are different for each pipe. So we take the minor losses from the pipes that we're using, just like we take the velocity from the pipe that we're using. So the first thing that we need to look at is we have a sharp entrance. And so for that 2-inch pipe, we know that that sharp entrance is going to be 0.5. Sharp entrances are always 0.5, exits are always 1. And then we have two 90-degree elbows that are threaded. So as I take a look at this, that first pipe is a 2-inch pipe. So 2-inch 90-degree elbow, so we'll have 2 at 0.95. And then we'll come back to this one here, but we have a sudden expansion. So we can either use the equation or we can go to our sudden expansion chart.